Hello, everyone, and welcome to part one of three-part video series about our solar system. My name is Mr. Martella, and these videos are being made for my Integrated Science 3 class at the New Brighton Middle School. So hopefully we'll be able to answer a lot of your questions in the coming videos. Part one, today we're going to talk about how we organize space objects, and we'll also take a closer look at our sun. Part two of the video series will deal with planets versus stars, the size of planets compared to each other and compared to our sun, and also the vast distances that we encounter when we're in space. The final part of the series will deal with the configuration of the inner and outer solar system. We'll talk a little bit about gravity and orbits. And finally, we will talk about our evidence for why we believe what we do about solar system formation. So hopefully by the time you're done watching these videos, you'll have a solid understanding of the universe, the galaxy, the solar system, and all of the satellites that are contained within it, especially the natural ones. So let's get started. First, some space basics for you. We need a way to organize the objects that we see in space, and we tend to do that based upon the orders of magnitude. So if we're thinking first of all about what exactly is space, where is the solar system, where are galaxies, where are what we see in space? Well, that's the universe. The universe is everything. Everything that we know of is contained within it. Okay? Now, the really mysterious part of the universe, or idea that's connected with the universe, I should say, is this idea that, there are really two parts to the universe that we know. There is the observable universe, that which we can see, and then there is the unobservable universe, that which we cannot see. And I will say this, there is much more to the unobservable universe than there is to the observable universe. So the things that we're going to be talking about obviously are within the observable universe. Now, within the universe, we have different galaxies, all right? Galaxies are large clusters of planets and stars and other natural satellites that are scattered throughout the universe. So our galaxy, the one that we live in, is called the Milky Way galaxy. And, there are many, many other galaxies out there. The one that is closest to us is called Andromeda. Okay? Now, within the galaxy, or within those galaxies, we have solar systems. All right? And solar systems, I'll refer to them as planetary systems. Sometimes you'll hear me refer to them as cosmic neighborhoods. All right? These are groups of planets and other objects that are orbiting usually a star. All right? So after we get down through the level of the solar system, we come to the planetary level. All right? And so that's the way that we organize our universe from largest to smallest. All right? So the universe here, within the universe, we have galaxies. Within galaxies, we have solar systems. Within solar systems, we have planets and stars and things like that. Okay. Now, I've also included a short animation here to show you a little bit about our Milky Way's three-dimensional structure. All right. So if we play here and you take a look here, this image is going to rotate, and you can see our solar system. You see this little sun right here. It's It's moving around. That's where our solar system is with relation to our galaxy. Okay. And once again, we call it the Milky Way galaxy because from space, it gives off this sort of milky white glow. Okay. So, how do we know what's out there? I know that, a lot of folks out there are kind of have taken the attitude that I'll believe it when I see it. Okay. And well, we have some images here. You see a panoramic image that the Mars rover took in June of 2017. That particular rover died last year. And so it is no longer sending back information to Earth. But you can see here the beautiful Martian surface in this image that was sent back by the rover. We had Juno, which is a satellite that explored Jupiter for quite a long time. And Juno's mission was very interesting. It gave us a lot of data about the largest planet in our solar system by doing some flybys, taking pictures, doing different measurements and things like that before it finally crash landed into Jupiter's surface, actually not very long ago. All right. But if you look here, this is an image of Juno when it was about 1.25 million miles from Jupiter. At this point, it was traveling about 70,000 miles per hour relative to the Earth's speed. But we got back a treasure trove of information about Jupiter's surface, about its conditions, about its moons. A bunch of information came back from Juno that we're currently still analyzing and still trying to make sense of. So we realize that we have the tools to study these planets and these stars. Well, what have we learned about our sun so far? Because one thing that we're going to continue talking about throughout this course this year is how everything here on this planet starts with the sun. If it wasn't for the sun, we would not be here. It's that simple. So let's take about 5 minutes here, and I'm going to play this video. Take a look. I think you'll learn some things.
While billions of stars are scattered throughout the universe, the one at the center of our solar system plays a special role for us here on Earth. Our sun formed about 4.5 billion years ago in the Milky Way galaxy's Orion Spur. It was born when a cloud of dust and gas, known as a solar nebula, collapsed. And in the middle of this formation, matter condensed into a burning ball of gas that became our sun. The sun's fiery nature, along with a tremendous gravitational pull and an extensive magnetic field, helped it to become the heart of our solar system. The sun can be divided into 6 layers or regions: the corona, the chromosphere, the photosphere, the convective and radiative zones, and the core. In terms of atom count, the sun is about 91% hydrogen, the sun's fuel, 8.9% helium, and 0.1% heavier elements, such as carbon and nitrogen. Due to the sun's extreme temperatures, these elements stay in a gas-like phase called plasma. In the core, temperatures reaching at least 27 million degrees Fahrenheit, combined with the sun's powerful gravity, fuse together hydrogen molecules to create helium. Called thermonuclear fusion, this releases an enormous amount of energy in the form of radiation, electricity, solar wind, and, as we experience on Earth, life-giving heat and light. Such volatility is contained thanks to the sun's tremendous gravity. It's strong enough to hold the solar system intact and is primarily due to the sun's size and mass. Our sun is the largest and most massive object in the solar system. It's more than 100 Earths wide and could theoretically fit all 8 planets inside nearly 600 times. It also contains approximately 99.8% of all the mass in the solar system. Because of this mass, the sun has a great pull on the fabric of space, creating a gravitational force that causes nearby planetary bodies to be drawn toward it. This gravitational pull allows the sun to hold together a system of 8 planets, potentially dozens of dwarf planets, at least 170 moons, and countless comets and asteroids. Without the sun's gravity, these celestial bodies would drift off into deep space. Another critical property of the sun is its magnetic field, which encapsulates the entire solar system. Called the heliosphere, this force field protects the planets from harmful cosmic radiation. It's caused by the sun's plasma pushing electrically charged particles toward the star's poles. This process turns the sun into a giant magnet. Although the sun's magnetic field is invisible to the naked eye, its effects are noticeable. On the sun's surface are dark areas called sunspots, which mark strong pockets of magnetism. On Earth and on some of the other planets, the sun's magnetic field interacts with their atmospheres, resulting in beautiful auroras. Despite its size and strength, the sun will not last forever. In about 6.5 billion years, it will run out of its hydrogen fuel, expand to envelop Mercury, Venus, and even Earth, and then collapse into a small star known as a white dwarf. In the meantime, the sun will continue to play a critical role in the system that bears its name. The sun's protective magnetic field, tremendous gravitational pull, and ability to create vast amounts of energy will protect, contain, and give life to our solar system.
All right, so that's just a little bit about our sun and how does the sun work? That's the biggest question here. We believe that the sun is about halfway through its life. It's about 5 billion years old or so, and we expect that it will burn and give off life-sustaining heat and light for another 5 billion years. So what powers the sun? Well, these two processes, nuclear fusion and nuclear fission, are processes that you need to be familiar with if you're going to understand not just the sun, but several different things, including nuclear energy, that we're going to talk about in this class this year. So, nuclear fusion, first of all, if we look over here on the left side, is here, think hydrogen bomb, the H bomb. It's when we take the nuclei of atoms of unstable elements and we fuse them together. And this releases a massive amount of energy, okay? The other process is fission. Here, think atomic bomb, the bombs that we dropped on Hiroshima and Nagasaki. And this is the same process that we use extremely safely in our nuclear power plants. Here, what we do is we actually split the nucleus of an unstable element, and that releases a lot of energy also. All right. Now, the atomic bomb and the fission process does not give off as much energy as the fusion process does. Okay. And so when we think of the sun, you think of fusion. It is fusing hydrogen atoms, and in the process, it's giving off all of this energy that we know as heat and light. So here's an image of the difference between the process of fusion and fission. And you see on the left, we're taking one atom and we're splitting it into two, giving off heat and light. And on the right side here, the fusion process, where we're taking two atoms and we're essentially combining them into one atom. All right. I hope you guys understand a little bit more now about how we organize space objects. Remember, we start at the universal level, all right? And then we have galaxies that are contained within the universe, solar systems that are contained within galaxies, and then we have our planets and our stars, which are contained within solar systems. We'll be back really soon with part 2 of our solar system. Thank you guys for watching.